Right. Good morning, everybody. Welcome to this problem-solving session of our course, Advanced Quantum Mechanics. What will we do today? As far as lectures are concerned, we are in dissipative quantum mechanics. And today, Kars will give us a presentation with kind of very simple meaning. Namely, we're gonna run some foolproof take on dissipative quantum mechanics. We will take a damped oscillator in the limit of weak friction, and cause we will compute the dissipation in this oscillator in two ways. First way is Fermi golden rule applied to the Hamiltonian, which we use to quantize damped oscillator. And then the same calculation will be done by classical means, and the results will coincide. And that will be revealing. What also will be revealing, you will be demonstrated simple methods, which you also can master, apply. There's nothing in this presentation which you would not be able to do with your hands, with your mathematical muscles. Right. That will be first part. Second part will be, so to say, free program. I will be ready to answer any questions concerning the course, practical questions, philosophical questions, special questions, questions concerning homework. Probably I would not ready to answer, but to remind, there is a short package of homework available for your enjoyment. Very good. Now I will switch to Kars. I will put him in focus. Let's see, how can I do this? Yes, I guess I know how to do this. Spotlight video. Kars, you're ready. Let's go.
Yes.
Does it work?
Yeah, can you see my screen? I think you can, right?
Yeah, no, I have to stop my own share. All right, and now we can see your screen.
Okay.
Excellent, good.
Good.
So please go on.
Yes, I'll talk about problem 27, dissipation through Fermi's golden rule, and I'll look at the do a quantum calculation and classical calculation. And we're doing this for the damped harmonic oscillator. So yeah, well, the harmonic oscillator, everybody knows what it is. It's just this potential here. And damped means that you have a friction force. So here you have a friction force that pulls on the particle, and therefore it loses energy to the environment. And we're going to calculate at which rate this happens. So the energy loss per time we're going to calculate. We're going to do it for the quantum case and the classical case. So let's start with the quantum case. Yeah, we're first looking at the harmonic oscillator here. So the harmonic oscillator, you have this potential, and you have these discrete energy levels. And yeah, well, okay, so this is the harmonic oscillator. So let's add something, a boson bath, to which we can dissipate energy. So we're going to add this friction force later, but here we have a boson bath, and yeah, it has modes k you can occupy with a certain energy, h bar omega k. Okay, so let's add a friction force. Well, this is the coupling. This is the friction force, and you can create or destroy particles in a boson bath. And with this X, you can go up and down the ladder of the harmonic oscillator. Yes, so that's all. This whole picture here is the damped harmonic oscillator for the quantum case. You can have transitions like emission here. So you dissipate energy to the bath, and you can also receive energy from the bath. So that's written here. So the energy is emitted here, and you're going up the ladder here. Okay. Now we're going to treat this coupling as a perturbation. So this means that we can calculate the decay rate using Fermi's golden rule. Well, here we have some prefactor. You have final states over which you sum, and some initial state. You square that, and this is just energy conservation, this delta function. And these I and F, there are eigenstates of this Hamiltonian, because this is the unperturbed Hamiltonian. So that means that we have initial and final states. There are eigenstates of that Hamiltonian, and the initial state is just given by some state n of the harmonic oscillator and some other state big N of the boson bath. And this state big N consists of all the different modes with a certain occupancy. So you have mode 1, which has occupancy N1, mode 2 has occupancy number N2, and so forth. And the initial state energy is thus given by just the energy of the harmonic oscillator plus the energy of the boson bath. And this is the sum over the energy of all these modes. So here you have the energy of mode 1, this is the energy of mode 2, and so forth. And for the final state, we do the same, but we change the labels here. So you have states little m and states big M. These states little m are also states of the harmonic oscillator, and state big M are eigenstates of the boson bath. All right, so we can now plug that in, and you just plug it in here. So you have this is the initial state, this is the final state, and then if you replace H coupling by XF, then you find that you have this equation here in the last line. Okay, very good. So you have two processes going on here. You have emission and you have absorption. So you have this blue arrow for which you are in the state N, and then you transmit energy to the bath, and then you are you lower your energy of the harmonic oscillator. You go down the ladder on the harmonic oscillator, and the state in the bath gets some extra energy. So the initial state is just the state N here, and some state N, big N in the bath. And the final state is you went down the ladder, so you have N, you're in the state N minus 1, and the energy, and the state M is the state which has gained this energy here. Okay, so for that state, we know that this expectation value squared is just Cx squared times N. And for absorption, it's the other way. So you are in this state which has a larger energy, M, in the bath, and then you emit energy to this state N. Then this state N absorbs this energy, and it goes up the ladder. So it's, the final state is N plus 1. And then you have here the state big N, also in the final state. And for this process of absorption, the matrix element squared of this is Cx squared times n plus 1. We can just get this by using the relations for the creation and annihilation operators. Okay, so we've split up calculation into two parts. So let's start with emission. So remember we had with this relation for emission. So I just plug that in, then you find it, you get this prefactor here, and Cx squared times 2 pi divided by h bar. And we still need to calculate this part over here. So we need to calculate this matrix element. And yeah, so this F, you can either raise or create or destroy a particle in this state n. So that means that I need to compensate this state m here with a creation of a particle, which is done here, or an annihilation here. So you lower the number of particles in a certain mode. And yeah, so we split that up again. So you have this matrix element here and this one here. And then we plug in the energy. So here we have EM, which is just the energy of n plus 1. And in the other case, we have that the energy is lowered by 1. All right. If we now, this is just, so if we let this be there to work on nm, the state is, you get this square root nk plus 1. And if you square it, it becomes just nk plus 1 times the delta function here. And for the other parts, you have nk minus 1. This bx on is m, so you get square root in front of n. And if you square it, then you get this nk. And then, it's not, maybe this is in the way here, but going from here, this last line to there, I use that we can write the delta function of delta alpha omega is 1 over alpha times omega. So this factor of h bar comes in front and cancels against this factor of h bar here. And I use that, I assumed here, that omega and omega k are both bigger than 0. So that means that the argument of this delta function can never be 0, it's always bigger, and therefore it will always be 0. Okay, so this is the emission part. In absorption. So remember we had that for absorption, you raise your state on in the harmonic oscillator by 1. So you have this prefactor here, which is written down there again. And again, we do a similar calculation, but now we sum over n, and the delta function also changes. Actually just a sign change. So if you just plug in the energies, then you find that this comes out. And again, we sum over the states n, and now the final, the initial states are given by the state m. So creation here must be also compensated by the addition of a particle in this state here, and annihilation of a particle here in this state must also be compensated by annihilation of a particle here in that state. Good. And then you find that you get mk plus 1 here in front of the delta function, and just mk in front here. And you can also rewrite this back into a form which just involves n. So in this case, we have that n is equal to mk plus 1, so we just can plug in nk. And here n is nk minus 1, so mk is equal to nk plus 1. And again, assuming that only that omega k and omega are, there's a question. Could you maybe elaborate on how you apply the caps? Yeah, so I let this B dagger M work on the state MM, and yeah, then you get this square root MM in front. They have this the bra and the cat working together, which gives together the delta function. So you get the delta function of K and M, and therefore so going from here to here, from this here to there, I also use that the delta function for or that K is equal to M. Does that answer your question? Or yes, good. All right. Where was I? Yeah, here. So yeah, so this will be fine for absorption. Dissipation is given by the difference between absorption and emission. So if you just plug in the numbers, or just what we found, we have that's equal to this here. So you just get this delta function times pi times ck squared. And well, then we use some relation from the book. So by definition, you say, this j omega is equal to this thing here. And in this case, this is equal to omega times gamma times the theta function, or the Heaviside function of omega. This gamma here is the friction coefficient. And we are going to assume that it's independent of frequency. So yeah, if we write out the Cx squared, then in the end we'd find that the decay rate for dissipation is given by this thing here. So you have minus gamma divided by m. Okay, so we're almost at the dissipation. So the power of dissipation is just given by multiplying the decay rate by the energy. So you get minus E times gamma, and then that becomes minus gamma divided by m times E. So we have the dissipation only for positive frequencies. Okay, so that's the quantum result. Now let's look at the classical damped oscillator. So this is part B of the question. So we can compute the energy dissipation as function of energy from the classical equations of motion in the limit of small dissipation. Okay, so this dissipation P is given by the expectation value of the work, the derivative with respect to time of the work, and you average over some interval. This is given by this integral here. You have this F, which is the friction force times the velocity, and the friction force is minus the friction coefficient times x dot, and that's what's written here. So yeah, the power is just given by gamma times x dot squared, and then you integrate over some time interval. Okay, so we want to calculate this x dot from the equations of motion. So that's our objective. The classical equations of motion will give us x dot. And we need to do this in the limit of small dissipation. So that's for small gamma. So actually we're doing a sort of, we're expanding this gamma. We're doing a series in gamma for gamma close to 0. And then, we also need to compute the dissipation as a function of the energy of this harmonic oscillator. Okay, but first let's start with the equations of motion. So in general, or if for the classical case, it just looks, the Hamiltonian looks like this. You have some kinetic term, Then you have the potential. Then here this friction force. And this friction force, yes, it's the friction coefficient times the velocity with a minus sign. Yes, so you have this potential, and then you have these two forces working on it, the friction force and the force due to the potential. But since we're doing an expansion in this friction coefficient, you can actually do the calculation without this friction force. It's a bit of a, yeah, maybe a leap, but for determination of x dot, it doesn't matter. You can also do the whole calculation with the friction force turned on and then later do the expansion. But as it turns out, it will not, it will not matter for the answer. So we can just, do the whole calculation without the friction force here. And then the Hamiltonian is just given by this. Now, we can obtain the equations of motion by doing this here. So P dot is minus dH dx, and well, we can see that it's just minus AX, and X dot is dH dP, and that gives you P divided by M. So if I take here the time derivative of this X dot here, you get X double dot and P dot here, and P dot is equal to minus AX. So if I then take it all to one side, you get X dot dot plus A divided by M times X is 0. This is the differential equation we need to solve. Here I substitute this A divided by M by omega 0 squared. And then we're going to, we know the solution to this. So you can say xt is just some coefficient we don't know times e to the I omega t. We can plug that solution in, and then together with these boundary conditions here, so at time 0 you don't have any momentum and also don't have any velocity, and you start out at some position x0 somewhere on the harmonic oscillator. Good, that gives you these solutions. So xt is x0 times the cosine omega 0 t. Well, then it follows from that x dot is minus x0 omega 0 times the sine of omega 0 t. And using the relation from the between x dot and p, you find that p is equal to this here. And remember, we want to calculate the dissipation as a function of energy. So we also need to calculate the energy. So that's just given by this here. So p squared divided by 2m is just the kinetic term plus the potential term. So this sine squared here comes from this p here, p squared, and x squared here comes from, or this cosine squared here comes from x, as you can see. Good, and this is always 1. So the energy here is constant in time, which also makes sense because you don't have any dissipation, so you cannot lose any energy. So if you start out in some position, you will just go back and forth, and you cannot lose energy because there's no friction. So the energy is constant in time. Good, now we can calculate the dissipation here. So we need to perform this integral. This is just, you just need to do it. This is just integration, basic integration here. So you find this integral is t divided by 2 minus the sine 2 omega 0 times t divided by 4 omega 0. And this t cancels again this one here. So that gives you this term. And this sine here, well, this period is given by pi divided by omega 0. And so this it's always 0. this sign here will always be 0 for this. So that's why it doesn't appear here anymore. Okay, so then we have the dissipation or the power in here, and we need to re-express it in terms of the energy. So on the previous slide, we calculated the energy as given by this here. So if I plug that back into the power, you find that the power is minus gamma divided by m times this energy. And okay, so question C, find to explain the correspondence between the classical and the quantum result. Well, we find that it's exactly the same. So both the quantum and the classical result give the same answer for the dissipation energy. And yeah, that's also the summary. So what we've done, we have calculated the dissipation with Fermi's golden rule in the quantum case, and we looked at these different processes of emission and absorption, and that gave us this dissipation. And then we also did the calculation in the classical case. We just start out with some the damped harmonic oscillator, and you from the equation of motion you derive x dot, and from there you calculate the power. And yeah, unexpectedly we found that dissipation is the same in both cases. Okay, so yeah, thank you for your attention. If there are any questions, I will be happy to answer them.
Question, please.
Is the similarity between the quantum answer and the classical answer, is that due to some more deeper symmetry, or is it just a happy coincidence?
I don't actually, I don't know if it's due to some deeper symmetry or something, but yeah, well, maybe you can just see it as that this dissipation is sort of similar to giving energy to some boson bath. That's similar to just friction with the material, and yeah, it's basically just transfer of energy. Maybe that's why you get the same sort of answer. But
Perhaps I can kind of interfere here. Look, quantum mechanics is in fact a kind of parasite on the body of classical mechanics. All physical model situations which we use have classical limit. Particle in a potential, oscillations of a field, electromagnetic field, or whatever, waves at the surface of water. Any physical situation, any model can be formulated in classical terms and can be solved by classical means. And it means that there must be a classical limit in any problem. Sometimes this limit is pretty straightforward. So for us, we are working with oscillator. And classical limit corresponds to big energy to higher levels of oscillator population. Then we can treat oscillator as classical one, and that's where we see the correspondence. it's a bit surprising that correspondence is really seen up to the level of single quantum, but well, it should not be really very surprising. But for any system, and this is important, one should be able to find classical limit. And it should correspond to classical reasoning. The point is that quantum mechanical way to compute this classical limit and classical equations by themselves can be very different. For instance, one could take atom, and there one would have to write Newton equations for an electron in the field of proton, somehow solve these Newton equations, and find the correspondence of the solution to quantum mechanical states. For an atom, this correspondence is found again for high states, high in energy, very close to the edge of bound states for atom. So if you have an atom, you can start with a ground state, which is very small, which is very close to the nucleus. Then you go high in energy, the states become bigger, bigger, and bigger, and then we can treat them in classical. Okay, then you have to confront classical equations and quantum equations. They're very different, but they should provide you the same result. So something like that has happened now. We actually had to find this correspondence. If you would do something, if you would get some other answer, for instance, suppose you would get for quantum answer 2 times gamma divided by m times energy, or that would signal a mistake. That would signal a fact that in fact we did not quantize the oscillator correctly. Right? So we have found correspondence, and this is kind of foolproof check. Now we know that at least our way to quantize the oscillator works in classical limit. All right. Yeah, Mohammed called it correspondence principle. Yeah, it is frequently called correspondence principle. So there must be a limit in which quantum system would correspond to a classical system. But equations to describe both limits from quantum and classical way can be different. Very good. There was a question of Isaka to you, Kars. Can you please look at it and answer?
Yes. Can you explain again how we solve the equation of motion for FF is 0? Yes, I can explain. So let me see. Yeah, we're doing this expansion in, we're doing this calculation in the limit of gamma is small. Dus you can calculate x dot just for the full for gamma not equal to 0, and then later expand it. So then you get as a first term something that's just, I don't know, yeah, it's just x dot for gamma evaluated at 0, and then plus some corrections on second order term, which is proportional to times gamma. So this derivative with respect to gamma, and then evaluated at gamma is 0, and then plus higher order terms. But this power here is already proportional to gamma. So if you would do the whole calculation and then expand in gamma, you'll find that this is just equal to x dot around squared around gamma is 0, and then plus something that's gamma times the second Taylor term, so some other correction here. So this term here is proportional to gamma. This last term is proportional to gamma squared, and we neglect that. So that's why we can take f to be 0. I mean, you can do the whole calculation, and then with this gamma not equal to 0, and then in the last line here expand your answer. But yeah, it won't matter. So you just get corrections that are order gamma squared. Maybe it's easily, yeah, that's, I've done the calculation, so I know that it's, you don't get any, oh, this should be gamma squared. So I know that this works, but I thought it's more transparent to show it, to show to derive the solutions here for gamma is 0. It's more transparent, but in the end it doesn't matter. I hope that answers your question. Okay, great.
Good. Are there further questions to Cars? There is opportunity to do it now. All right, sir. I don't think so. So let me remove Cars from the spotlight. Does it work? No, eventually it does not. Yeah. Anyway, I should start my own window, perhaps. Right. Good. So here am I, and you can ask questions to me. So I would like to hear your questions about the course, practical questions, organizational questions, questions concerning any topic of the course. I would not like perhaps at this time to answer concrete questions about homework. We will still have a session about this particular package of homework, but I would gladly answer general questions. Is something more known if the exam will be online? I guess with a probability of 99%, the exam will be online. Remaining probability, it's not very likely to happen. It will be the case only if the general political situation concerning the measures about coronavirus would change suddenly, right? Yeah, for instance, you have heard about the demonstrations in The Hague. Suppose these demonstrators just storm parliament, will take power, will change everything. Everything can happen. Then perhaps you would have exams offline, but I don't see it happening. Good. Then how about the way exams will be conducted, it is also not very certain now. Let me explain more about this. I have some ideas how to do this examination. I can share this with you now. But that's first, frankly, it's not very clear now without experimenting how practical are my theoretical ideas. So perhaps we won't be able to implement everything which I would like to have. Second, and more important, in fact, it goes like this. Every teacher should make a proposal how to do online exam. And there is exam commission of our study Richten, our educational direction, which has to look at each proposal and actually endorse it or reject. So it's not very certain now. Is it a good topic to address? Anybody is interested in this topic about the exam? Why don't you respond yes or no? Shall I talk more about a possible way to conduct online exams? Yes, 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 yes. I see positive responses. Good. So let me outline how do I see this. Again, perhaps it can be changed because we won't be able to implement everything, or perhaps this exam commission would reject our proposal. Right. It looks like this. Everybody. First of all, we want to keep it as similar to of usual offline examples as possible. So to stress similarity, there will be the same structure. There will be open question, a problem to solve, very similar to your homework, consisting of, say, 5 points. And you would get certain number of score points. Let me see, say 5 per each point. First points will be easy. Further points will require calculations, and there will be perhaps 6 points, a bonus point. Right. So it is like in the exam samples, which you can find in the bright space. First part. Second part, multiple choice questions. You get 25 multiple choice questions. You will have to mark correct answer. And these questions will check how good you've been looking at lecture materials. The rule is that all correct answers can be found in slides of the lectures. And there are incorrect answers which look correct, so you have to kind of show that you really understood what you have read, what you have listened to in the lectures. Right. So I guess we still have same structure of exam tasks. A different question, how to implement it online. And yeah, that's important detail. At the moment, it looks that we will randomize these formulations of the problem. That concerns multiple choice questions, and that concerns open question. So since we could not really, watch everyone making this test, we will have to make randomization. So everybody would get an individual task. But that's, of course, not at the conceptual level. Like if we talk about multiple choice questions, it would just mean different orders. For some students, correct answer to question 7 will be A, for some will be B, for some will be C. All right? Questions would be the same, but their ordering, numeration will change completely, will be randomized from student to student. And in a similar way, we will randomize open choice questions, so the content won't change much, but we will find the way to make it individual for every student. Then at some stage, perhaps precisely at the same time, which is scheduled, which is easier, we will distribute the tasks. And then within given time, say 3 hours, I guess it's also a reasonable time, you will have to return these tasks to us via Brightspace. So what you have to do is to have a stable internet connection at this period of time. And that's it. Other questions concerning this information? Did anybody of you made already online exam? I mean, in April, perhaps, or in March. No, nobody? Right. Sophie, Sibren. So, Sophie, how did you like it? Was it kind of more stressful, less stressful, the same? More stressful, said Sophie. Can you explain why? Perhaps you can switch on your microphone and tell us a little bit, like a minute, about your impressions. Or you can type if you wish. Sophie? Oh, okay. Neighbors of Sophie have been renovating their bathroom precisely at the same time. Yeah, must be noisy. Yeah. So there will be always incidents like this, or if you kind of have influence upon your neighbors, perhaps you can talk to them and make good appointments that you have examination. Yes, there's a question from Isaka. Are there going to be oral questions following the written part? nor we don't plan oral questions. We could, but there are kind of, frankly, too many of you to do so. What we can do, again, it's a possibility, it's not certain. We can request after examination, say within a day, we can request an oral appointment with you, like Zoom session, kind of to check whether you understand what you have written in your answers. I personally don't like it, but colleagues say it's very efficient against that would increase the way students would handle the tasks. You understand me? So we don't plan oral exams. That will be very difficult to implement, and it will really require much time. Perhaps we will finish the exams only in 2021. I don't think you would like to wait that much. So there will be a written examination, but there can be a possibility of Zoom appointment after all if we have questions about your answers, about written answers which you submitted. Again, we want to keep submission as easy as possible, so the photographs made by your telephone or whatever mean and sent to Brightspace would possibly suffice the way you do it homework. If you have kind of time to bundle it into a PDF file, I wouldn't say you get an extra score point, but we will really appreciate this because it will simplify quite a bit our effort. It's much easier to handle a single PDF file than a set of photos. Sure, it won't affect your mark, of course, but it would be kind of a sign of good politeness from your side. Very good. More questions about examination, about the way we conduct it, the way we see it. I do not see any questions. Perhaps to add a couple of words of about examination, we really want to make it uniform in all the Dutch tradition. So the exams vary, of course, the exam tasks vary, of course, from year to year, but the structure remains the same. And you can learn a lot concerning practical skills, not about the course, but about passing this examination, just inspecting old exams, which are kind of abundant. You can find many of them at Brightspace. And I guess if you look at one and two, the total structure will be clear and it won't come as a surprise for you. Fine. Very good. So I expect we have said everything about exam. Any other questions concerning the topics of the course, concerning the way we organize lectures in this another time? Concerning presentations, concerning everything. Yes, the question is, will the grade for the homework will be posted on Brightspace? Or eventually, I don't know precisely, since we have changed the way it goes. I don't think it will be posted for everybody, but there's a way to see your mark at the Brightspace. So I guess our instructors would implement this by this time. And not for former set of homework, because it didn't go through Brightspace. And again, it's not a grade which you get from homework. It is a number of score points which you have earned. So in total, for all homework done, you cannot earn more than 200 points. If you did more, it is rounded to 200. And these 200 points, they count for 15% of your final grade. All right. Good. More questions? I would like to have more. Let me just count 2 minutes and then close the session. So, but I would love to have a question meanwhile. All right, sir, if there are no further questions, let me conclude this session. Thank you for attending. Thank you for letting me to feel your presence. I like this course very much. I like you to be present. Then till Thursday, till next lecture. Bye.